Hi everyone. So in this lesson we're going to talk about acceleration. Though we're not going to get into too many equations, that'll be more for next lesson. So here's just kind of an introduction, so hopefully it shouldn't take too long. So by the end of this video, what you should be able to do is define acceleration, explain its relationship to velocity, and interpret graphs of velocity versus time. And then you should be able to create, use an interpretive narrative, so words, mathematical and graphical representations for linear motion with constant acceleration. So things may not always be moving at a constant velocity. That's what we've talked about last lesson, so moving with a constant speed in a certain direction. But this may not always be true. So there's three ways we can kind of tell if something is not moving with a constant velocity. If it's speeding up, if it's slowing down, or if it's changing directions, which is kind of something we'll touch upon in a different unit. We'll kind of focus on the speeding up and slowing down for now. But if velocity is changing, that means our object is accelerating. So if you look at these kind of motion diagrams here on the right, option A here is moving with a constant velocity, whereas B and C are accelerating, right? So in B, the object's speeding up because velocity is getting faster and faster, so it's speeding up in a certain direction, whereas in C, this object's slowing down. So they're both still accelerating. I am going to avoid using the word decelerate. I'm not a fan of it. Most people use it incorrectly when they're trying to use it in class, so I recommend that you don't use it either. It's unnecessary. You can either say that the acceleration is positive or negative depending on your coordinate system, and that is completely adequate. We'll get more into that later. So just as a reminder, when we're dealing with velocity, velocity is the rate of change of displacement. So remember, rate of change means that it's quantity that changes with respect to time. So for velocity, it's rate of change of displacement. Acceleration is the rate of change of velocity. So kind of very similar quantities here. I put here a formula for average velocity. So it's going to be your change in velocity over the change in time. And that's over the time that change of velocity occurs. Looking at dimensions here, we've got in our numerator velocity, so that's meters per, or distance over time. And our denominator, we have just time. So we have distance over time divided by time, giving us distance over time squared, which would then have SI units of meters per second squared. All right, so if you look on the right here, I have a graph of position versus time for an accelerating object. All right, if you notice here, we do not have a straight line anymore going on. So this blue line is, or excuse me, this blue curve is the position versus time graph for something that is speeding up over time, accelerating. So what if you wanted to find the velocity of this object? Well, you know the velocity here is not constant, right? Because the object's speeding up. So the best we can do is actually find what's called the instantaneous velocity. So velocity at a certain moment. So let's suppose a problem here asked us to interpret this graph and determine the velocity when the object is after the object has traveled 20 seconds. So you see here, this red line helps us out. So we can draw a tangent line, right? So we're drawing a point. So at the 20-second mark, we draw a tangent line to the curve, and if we find the slope of that tangent line, that will tell us the instantaneous slope, the instantaneous velocity at that point, which is pretty neat and kind of handy. We probably will not use this all the time, but I have seen questions like this asked on the AP exam, so it's a nifty tool to kind of think about. So let's look at this position versus time graph and kind of try to describe what's going on here in terms of words. Right? So our object, whatever the object is, starts at some positive location based on however we define our coordinate system. So it starts at a positive location and starts heading towards, I guess, some negative location. So maybe let's describe something as maybe moving to the right and to the left. So let's say rightwards is positive. So our object here starts at a positive location and is moving leftward in the negative direction. So in segment A, the object is moving with a constant speed. You see here the slope is straight, and they're moving towards where we're calling 0. And we're still moving at that same speed as we did in A in part B. All right, and we're still not even just same speed, same velocity, to some negative location after segment B. Then we start moving rightward again, all right, because we see here in segment C that our change in position is becoming more and more positive, so the velocity is positive. We also just look at that by the slope. We have a positive slope here. But we're doing that a little bit more slowly than we did in segment A and B. So if we kind of look at the slopes here of A and B compared to the slope at C, the magnitude of the slope, we see that it's a little bit steeper for A and B. So we're moving a little faster in that segment than we are in here. Right? So we're moving rightward in segment C up to wherever our 0 location was. And then we see here in segment D and E, we have acceleration going on because our position versus time graph is curved. So in segment D here, all right, we're moving in the positive direction, all right, so our velocity is positive. And velocity is positive, but also our change of position is getting smaller and smaller over time. Right? Eventually, if we look at our rise over run, our rise is basically 0 at this point. Right? So our velocity is, so we're slowing down in this region. All right. And then in segment E here, right, our position now is becoming more and more negative, right? We're heading towards the negative direction. So our velocity is negative in segment E, and it starts off near 0 and then gets faster and faster. All right, so that's kind of a way we can describe the motion of this object. So this is a position versus time graph. Now, we have to kind of think of positive quantities versus negative quantities when we're dealing with linear motion. So for example, if we say the displacement's positive, that literally means the object is moving in a more positive direction, whereas if displacement's negative, it's moving in a more negative direction. Doesn't mean that the position is negative. It means that it's going from a more positive location to a more negative location. All right, so that's a common point of confusion. So kind of what I mean by that is maybe we started at a location of 5 meters and headed to a location of 2 meters. That's a negative displacement because we're moving towards the negative direction. Now, velocity is actually very simple to think about whether it's positive or negative. If our object is moving in the positive direction, that is a positive velocity. If it's moving in the negative direction, it has a negative velocity. All right, so whichever way it's going, if it's going positive or negative, that's the direction of velocity. So I find that to be the easiest one to think about. Now, acceleration, if acceleration is positive, well, we know acceleration is change in position, or excuse me, change in velocity. What am I saying? Acceleration is change in velocity over time. So positive acceleration means our change in velocity is positive, whereas a negative acceleration means that our change in velocity is negative. Now, where this is going to become useful is kind of thinking of situations whether we have positive acceleration and positive velocity or negative and negative. So we can kind of have 4 different situations here. So let's suppose we have an object that has a positive acceleration and positive velocity. Right? So positive velocity means we're moving rightward, right? So we're moving in the positive direction, excuse me. So moving in the positive direction, but then also it's speeding up, because we have positive acceleration, which means our change in velocity is also positive. So those kind of compound on each other, right? So if you think of it as, let's say, rightwards is positive, which usually we do, that means our object's moving to the right, but also speeding up to the right. Now, kind of the next easiest thing that you might be able to think about is kind of the symmetry to this, which would be negative acceleration and negative velocity. So we'll kind of skip to that quadrant here. So negative velocity means we're moving in the negative direction. So in this situation, we're moving to the left. And negative acceleration means our change in velocity is also negative. So it's speeding up in that negative direction. So we notice here, both our velocities and our accelerations were both in the same direction, and those kind of compounded on each other. And the object was speeding up in both cases. That's always going to be true. We can also have the situation where one's positive, one's negative. So let's suppose we had positive velocity, so we're moving rightwards, and negative acceleration. So that means our change in velocity is negative, right? So that means our object is slowing down. Whereas conversely, we can have negative velocity, moving leftward, and positive acceleration. So our change in velocity is positive, right? So then that's also slowing down. So when the velocity and acceleration were different directions, it's slowing down. Always going to be the case. Now, kind of the last thing I want to touch upon is a velocity versus time graph. So these are also very useful. We can learn 3 things from these. We can learn what the velocity is. It's velocity versus time graph. We just kind of read it off the graph. We can learn the acceleration of the object, and we can also learn about its displacement. All right, so kind of what I mean by that. So let's look at this velocity versus time just graph. I kind of quickly sketched it. This is basically the simplest graph you'll ever see. Let's use some unit analysis to figure out what we can determine from this. All right, so here we can literally just read off the velocity at a certain moment in time. You know, look at whatever that time is, read over whatever that velocity is, we can read it off. All right, so that's simple enough. Let's see what the slope will tell us. All right, so we know slope is rise over run. Our rise here is velocity, so it's our change in velocity. Our run is time, so that's change in time. So our slope of this graph is change in velocity over change in time. Wait a second, we know that that quantity is called, that is acceleration. So the slope of a velocity versus time graph is acceleration. Right? Now when it comes to graph, another thing that we can easily find is the area of a graph. And what I mean by area here, it's always area under a curve. And under, I'm putting air quotes, not that you can see them, but it means it's the area in the region from the line or curve to our horizontal axis, right? Because we could also have a velocity versus time graph. That's terrible. In the negative quadrant. In that case, the area would be from our curve or line to the horizontal axis, whereas here, our area is in that region there. Anyway, so kind of getting to how to compute that, or what that area would tell us. All right, so here, area, if we were trying to find the area from here to, let's say, there, we have to deal with a triangle, but so that'd be 1/2 times base times height, but we're basically just taking, let's say we're trying to find some small area here, that's going to be meters per second multiplied by seconds, since it's my vertical axis and horizontal axis. So that's meters per second multiplied by seconds. Well, that cancels out, leaving us just with meters. So our area here tells us a distance quantity, and what it actually tells us is displacement, because we haven't learned a formula yet, but maybe I'll show you guys for the future. We're dealing with area being our change in velocity multiplied by our change in time, which we'll learn in, well, actually we can see this. This is actually going to be displacement. All right, and we can actually see that because we move our time over here, velocity is defined to be change in position over time. All right, so there. We have learned the equation. We'll have a different equation later on. But this is where I'll pause here, and I have one example left, and that should be pretty quick for the next video. All right, so hopefully that's helpful. Very interesting things we can learn from a velocity versus time graph.